All right, last day before the long weekend. After my class this afternoon, I'll be driving down there to our new house in Colorado where I will see Wes's grandmother.
Very cool.
Marilyn, something or other. I think that was it. She told us all of her grandkids who are here, and you were one of them.
Well, she might not be my actual grandmother.
Might not be
actual. Her pretty well. That's interesting.
Marilyn something. Well, she told us. No, I'm pretty sure it was Marilyn. Like Marilyn West or something like that.
Yeah, it was probably my very good friend. Probably grandma.
Okay. Anyway, so there's no school on Monday, which means that you don't have a reading quiz for Monday. You won't have a homework assignment due Monday night. You do have a homework assignment, though. It's due tonight, right?
Yep.
And then we'll have the next assignment that's due will be the pre-lab quiz for lab on Tuesday. And I'll see you in class Tuesday. Or if you're Physics 150 or 251, you'll be turning in that homework assignment. And then we'll be going on to do fun things. Everyone else will just be lab. Okay, to get started, we're down to 3. So, gotta randomly choose a card here to see who's going to come up. And it's DJ, Trace, and Leslie. And the problem that you get to demonstrate for everyone is not that, but this. And by the way, I should say, I couldn't hear it when I was sitting down, but when I was listening to the lecture afterward, I thought it was really cool that Ryan started by, let's say a little word of prayer.
So we are being recorded. That's nice to know.
Yeah.
Okay, suppose a woman flies 43 kilometers in direction 60 degrees north of east. So since we can draw on this, let's just add that in there. That'll be this one here. And then 28 kilometers, 15 degrees north of, why am I looking there? Shown in the figure.
So yeah, if you turn the pin around, it acts as an eraser, so you can erase the 60.
Yeah, you have to put
43.
43.
Yeah. That's cool. All right, so find her distance from the starting point in kilometers. Is that open?
No, just
Or do I just go into the angle one? How do I open each question?
You don't open them, you just do the work.
Oh, okay. So finding her distance. We need to take the components of A and of B, and then that'll give us the components for R, which we can then solve for.
Before they started, I was going to tell everyone there are 3 ways I know of to solve this, and so they're going to solve one, and I'm going to solve the other 2 ways.
Okay.
I don't feel like I'm undermining them at the end.
So for the first one, it'll be the sine of 60, and then the cosine of 60 for the y and x. Which are you plugging those in?
no. Wait, I mean, I don't have this in the quick mode. It is in
And then multiplied by the 43.
Yeah, okay. So there's your sign.
Okay, so the sine is 37.23
And cosine of that.
is 21.50. All right, and then we're going to do the same one for the other angle. So the sine of 15 times 28, which is 7.25.
There's your cosine.
And then the cosine of 15 times 28, which is 27.05. Okay, so then since they're both going in the same directions, all these components are being added together and they're all positive. So we'll end up with the sign of R being 8, 4, 4, 4. And that's the Y component. And then the X component will be 5, 5, 8, 4. So then if we do Pythagorean theorem, which refreshers.
A little bit slow on this.
It's all right. It's just because you're in the spotlight. 65.85. And that would be the distance in kilometers since everything's already in kilometers for R. So then the next one is about the angle theta north of east right here. Since we already have the components, we can just plug those in. It'll be the inverse tangent of the rise over the run.
Oops. Wait, you did it backwards. Oh no, that's the one again. It's tough for me to see.
Which is 42.49. Oh,
Just hit the one that says N.
cool. And those are the only two I see. So
Yeah,
that's it.
So right now you have it at 1. So what was the answer? You said 42 point.
Oh, I put it right here in circle.
Oh, okay.
42.49. But I can write it again.
All right.
Stay tuned for 2 more ways. Thank you for your lack of questions.
That was perfect. Thank you. Now, to make sure everybody followed the pieces they did, like I said, it was perfect. And if you know what you're doing, that's good. But I want to make sure everybody understands. So I'm going to take my first vector. I drew a line there that was parallel to the x-axis, a line there that's parallel to the y-axis to find the components. You can't just say the x component is the hypotenuse times cosine of the angle. Sometimes it's right. In this case, it was right for both of them. But in other homework problems for tonight, it's not right. So you have to actually look at the triangle. And in this case, we have the hypotenuse. And we had this angle here. And so the adjacent side was the x direction. And that's why cosine, the function that's adjacent over hypotenuse, was the one that gave us the x components. And so it was from this triangle that we were able to get a sub x and a sub y. As a general rule, we're going to be doing more than just 2 vectors. We're going to be doing lots of vectors coming up soon. A really good way to do this is to have your x direction and your y direction. And then I can have a vector equals, and for the a it was 21.5 in the x direction, and it was 37.23 in the y. And then for b, it was 27.05 and 7.25. And then you can just add each column. And so his 2 numbers he got here, the 44 was the sum of those 2 numbers. And the 48 was the sum of these 2 numbers. No, I had them backward. you also need to pay attention. So it's nice formalism to put them in a table like that, so it's easy. Sum of the columns, that's your total in the x direction. Sum of the columns, and that's the total in the y direction. And then to go from these numbers, you have the resultant triangle that was, this is poor drawing because the y component, well, it's not that bad, but so we had this triangle. So to find this angle, you know that tangent theta is equal to the opposite side divided by the adjacent side. So that's the function that's going to relate those two numbers. And so I take the inverse function of tangent theta. Inverse function does not mean 1 divided by. It means if I do the inverse function on the function, I'll get its argument. Now, to go with what you know, if I take the inverse of 1 over x, I get x. But if I take the inverse of tangent theta, it's not 1 over tangent theta. It's got to be theta. So if I do inverse tangent, which your calculators will have different ways of writing it. One is tangent minus 1. Another one is a tan. There might be some other common ones, but those are the two most common. So if I do the inverse tangent of the left-hand side, by the definition of inverse, that just gives me theta. But what I do to one side of the equal sign, I must do to the other side of the equal sign. And so what I'm going to have is theta is equal to the inverse tangent of the opposite, which was 44.48, over the adjacent. And so that's how they got to that equation. Right? This is trigonometry. We use a lot of trigonometry in this class. It's assumed that you know trigonometry, but I've got to review it because a lot of people don't have that assumed knowledge. So that's why I'm redoing parts here that they already did. Now, this here is the way they solved it. I said there's 3 ways, and I was going to show you the other 2. So what are the other 2? The most direct way, law of, let's do law of cosines. Some people may have never heard of the law of cosines. Some people will be like, well, duh. The law of cosine says if I have a triangle, any random triangle, and I label the sides A, B, C, and I label the angles with a capital letter that is the same as the side opposite. So since this, I have side A, the angle opposite to it is capital A. Side B, the angle opposite is capital B. Side C, the angle opposite is capital C. With that definition, then the law of cosine says that lowercase c squared equals lowercase a squared plus lowercase b squared minus 2ab cosine of angle C. That should look familiar even if you've never heard of the law of cosines. Because if it was a right triangle and C was the right angle, cosine of 90 degrees is 0. So if it's a right triangle and C is the right angle, then this is C squared equals A squared plus B squared, otherwise known as the Pythagorean theorem. So the Pythagorean theorem is simply a special case for the law of cosines. So now, how is that going to help me? If I look at this triangle, I know this angle is 60 degrees. I know these two sides. I know this is 15 degrees. Well, if this angle here is 60 degrees, if I were to make a right triangle here, what would that angle be? sum of the interior angles of a triangle is always 180 degrees. And so if this is a right angle, 180 minus 90 is 90. 90 minus 60 leaves me 30 degrees. So that's 30 degrees. This is 90 degrees. And then that last angle is 15. So my angle C is 30 plus 90, 120, plus 15, 135. So C is equal to 135 degrees. A was equal to 43 kilometers. And B was equal to 15 kilometers. And so I can say C squared is equal to 43 kilometers squared plus 15 kilometers squared minus 2 times 43 kilometers times. It's not 15? Where did I get? Oh, I got the angle. Ha! I was very consistent in being wrong. Thank you for correcting me before we get to the end. I say, now what is that? Someone comes up with another number, and then I'm like, wah, wah. Okay, so if you put that in your calculator, it is a shorter calculation than what DJ showed us, right? So it's more fun. Now, well, more fun. It's more fun to get it done quickly. The way DJ did it is the way that you're expected to do it. You don't have to do it that way, but it's the way you're expected. The reason is when you have like 5 different things you're adding together, it's the way it's going to work. This way is not going to work when you're adding 5 things because 5 things does not make a triangle make. And so you need to learn that way. But when you have something that can be put into a triangle, you have some other methods that you might consider to make life easier. So that is a second way, using the law of cosines. A third way is using the law of sines. Now, I didn't think this through all the way. I'm not sure if I have enough information to make this easy. But the law of sine says if I have the same triangle, that A over sine A equals B over sine B equals C over sine C. So if I know this angle and one side, I can find the other side. Now, the problem here, the thing I didn't think through is I do not know what this angle is or this angle. And so it's going to take a few steps. That is, I could use the law of sines to relate like I can't do the law of sines. I don't have enough information. So the law of sines is not a way I could do it. I didn't think about what angles I have. But sometimes that's going to be very easy for us to use as well. And this reminds me, I forgot who I was talking to this morning. Okay, I think it was Mira. On the exam, you're going to have an equation sheet. What's that equation sheet going to look like? If you go to Moodle and you go to the class, and I am just going to search because that's the easiest way to find anything in a web browser. Okay, so equation, it's not the calculus equations used in physics 251, 252. How about exam 1 equations, OpenStax? OpenStax is your textbook, so that's saying it's the exam, or it's the equations from your textbook for exam 1. And so this is what you'll get on the exam. Hopefully I will remember to come and, oddly enough, hopefully I'll remember to come in and change it so that's a vector sign. You would think okay, so perfect. Well, let me erase those because really some things are not perfect in life. Anyway, here's the equation sheet you'll have. So you can look at it right now. You can get used to it. There's not too much on it. What you have is, really?
I appreciate the jokes.
Yeah, something to keep you busy if you get bored. You have the kinematic equations with the tops of them cut off right now. You have the definitions of sine, cosine, and tangent. And then you have the two trig identities I just gave you, the law of sines, the law of cosines. Where's the Pythagorean theorem? Yeah, the law of cosines includes the Pythagorean theorem in it. So I didn't put it special because it's included with that. Something else that I didn't put here, if you need it, you just raise your hand, would be the quadratic equation. Right? If you don't have that memorized, don't fret and say, I can't do it, I need it. Raise your hand. Right? So if there's an equation that you think you need, raise your hand. If I agree you need it, I will give it to you. Back to our presentation. Now we'll see if the pen works here. Because, I mean, it did at one point. Hey, it still does. Excellent. A reminder about graphical addition. When you're doing graphical addition, the resultant of adding two things is the line that goes from where you started to where you ended. So in this picture on the right, the thing that's wrong about it, F1 plus F2 is done correctly. That's done the tip to tail like it's supposed to be. But the resultant there, the dark blue one, is going from the end of F2 to where we started. That's minus the answer. The correct answer needs to go from where you started to where you ended. So the correct answer needs to be this. Right? You see, this is incorrect because the arrow is going the wrong direction. Is that question right? Nope, just thinking?
No, yeah, just thinking.
Okay. One last thing to remind you of. In that problem, we had angles. I just found the value for the angle when I did it, but I believe that they said it right when they did their solution. If I have an angle that is, let's say, like this, this is y, and this is x, and let's say that I gave you this is 25 degrees. How can I specify the direction for that line? Okay, it'd be at 25 degrees, well, y of negative x, because I didn't give you north and west. It would be north of west if I'd given you north, south, east, west. The of is telling you where you're starting. So if it's y of minus x, that means you're going to start at the minus x axis and go toward the y direction. And of course, using the x and y of minus x means that the adjacent side is minus x, and the opposite side is y. And so when I'm doing my trigonometric relations, I have to think about which side's adjacent, which side's opposite. I could have just as easily asked for this angle, missed. I could have just as easily asked for the angle like this. That would be 65 degrees, what of what? Negative x of y, because I started at the plus y axis and went toward negative x. Getting those directions straight in your head is important. Otherwise, you'll make silly mistakes. You'll know how to do all of your math, and it's just going from the name to the actuality that caused the problem. I've already gone through sine, cosine, and everything. Remember, the sum of the interior angles of a triangle is always 90 degrees. And so this relationship right here helps you. If I know two of the angles, like if it's a right triangle, I always know the 90. So if I know one of the other, I can get the last. Very important thing to be able to do. Steps to solving a vector addition problem. First, select a convenient set of perpendicular coordinates. Notice I said convenient. Usually that's horizontal and vertical, but we will soon get to a place where that won't be the convenient answer. Break each vector into its component using sine and cosine. Add the like components, add the x's together, separately add the y's together. Then use the Pythagorean theorem to find the magnitude. Use your trigonometric functions to find the, tangent there, to find the angle. That's about all there is to it. I say that's about all there is to it. How do you get comfortable with it? Practice. So we're going to switch to a new topic. We have this gentleman kicking a ball. The path the ball takes, we call its trajectory. And the trajectory of the ball is not a straight line. When I throw the ball to, let's see, I'll throw the ball to Clayton, maybe. I'm not perfect in here. When I throw the ball to Clayton, it's not going to go on a straight line. I throw it to Clayton, I throw it up, it comes back down. So that trajectory is not a straight line. And so how do we deal with this? The answer is through what I mentioned last class, through independence of motion. The vertical and horizontal motions are independent. When it's in the air, we learned 2 lectures ago that we have an acceleration due to gravity of 9.8 meters per second squared down. It's going to have that downward acceleration. What's the acceleration horizontally? If the total acceleration is down, how much acceleration do I have horizontally?
Whatever force you have minus air resistance.
Okay, now DJ's getting a little complicated here. We're in physics class. In physics class, we make some unrealistic approximations that there is no air resistance. Right? What he said is a correct thing. I don't want people to say, what? It doesn't exist? But in physics class, unless you're told to account for it, you assume there's no air resistance. So sometimes we'll have it, but if it doesn't say anything about it, we'll assume it's negligible. We know it's there, but we assume it's small enough that it doesn't matter. Okay, so with no air resistance, the only force acting on it since he was going there is the force of gravity. What's its acceleration going to be horizontally? 0. The only acceleration is the downward acceleration. That's why it's convenient to break it up into vertical and horizontal. All of your accelerations in the vertical direction, none in the horizontal direction. And then we solve the vertical and horizontal directions as 2 separate problems. So let's do that. Oh, first we have to play. Now, as luck would have it, I can write on this today. But because I can write on it, I can't play. This is an animation. So I prepared beforehand, so I knew what would happen. And hopefully this now opens, yes. When I tried to open this before class, it wouldn't open the folder. That's why it's not already queued up, because it wouldn't open the folder. Because I am just that kind of lucky. So let's give that a second. I'll talk about what this is. This animation, come on, allows me to change the angle and the speed of the motorcycle jumper. And so we're going to change his angle and speed and see. You know I double-clicked it, right? I mean, it's got to be opening. It's going. Oh, goodness. I don't want to do that. I don't even know my password. And I didn't bring... Life is full of pain. I didn't bring my phone. I don't know the password. It's some convoluted password that they gave me. So I can't do this. I can't show it to you. And it's my fault because I set it up so it always loads that when I start PowerPoint. Note to self. Don't do that. Well, what it's supposed to do is allow me to hit play, and then it shows the motorcycle jumping. And as you change the angle, the distance that... Oh, I've got to change it back so you can see it. Hey, wait. Okay. Please, something work today. I hit play. Yay, look at that. Okay, so he overshot. He failed. Evel Knievel just broke his back. Again, the 20th time. You guys didn't grow up with Evel Knievel, I know. Jump in the Snake River Canyon, big time. Okay, so he went too far. How can I adjust to make him so he doesn't go as far? Okay, adjust the angle. Which way should I adjust it? Okay, Nathan said down, so I'm going to adjust the angle down. So let's go for somewhere around 40 degrees. See what happens. Reset, play. Still overshot. Let's go lower still. So now we're about 30 degrees. Success, right? So making it a flatter angle worked. What if I'd made it a larger angle? What would have happened then? Yay, successful. Which one of those two trajectories would you prefer if you were the rider? The lower one. Why?
Because less force coming down.
Okay, you don't hit the ground with as much downward speed, hence, like I said, less force. Once again, we haven't talked about force, so I try to minimize talking about that. But it's going to be a lot more painful here with the hard landing. So the flatter one is better. Now let's go back to 45 degrees. Let's say that our ramp is fixed. We can't change it. It's the last minute. What else can I do to make me go a shorter distance? Okay, if I slow his butt down, come to slower speed. Ooh, just a little short. A little faster here. There. Muy bueno. So you can get there with different variations. Notice there were two different angles that would get there. Something that a lot of you have probably learned is that 45 degrees is the optimal angle. How many people had heard that? Okay, 45 degrees is the optimal angle for distance if you are landing at the same elevation you start at. The textbook, in fact, has a range equation that's how far will you travel if you're at 45, or actually any degree angle, if you start and end at the same elevations. If you start and end at different elevations, 45 degrees isn't going to be the right angle for the largest distance. In fact, physicists, because we do these kinds of things, analyze sports a lot. And so a physicist analyzes basketball. So you're shooting a basketball. What angle is best for you to get the longest shot with the same force, right? Because you only got so much strength in that wrist. You know, if you shoot it flat, obviously you're going to have to shoot really hard. Shoot it straight up, you have to shoot really hard. What angle is going to work best? What do you think? Well, it turns out the answer is if you shoot at an angle so when it gets to the height of the rim, it's at 45 degrees, that's going to give you your optimum distance for how much strength you have. And it gives you the most flexibility, like if you're a little too hard, a little too soft, still the most likely to make it in. Also, if your angle's off just a little bit, still the most likely to make it in. So it turns out that that angle is the best angle for all of the significant factors. So you have the most margin for error if you shoot at an angle where it's going to be 45 degrees at the height of the rim. Just so you know, because we physicists, it's the kind of thing we do. Yeah. Now, Sebastian Janikowski, for the first time ever, faced the Oakland Raiders in the NFL last night. And, of course, he was far better than the scrub we have replacing him. Some guy named Nugent. Was it Mike Nugent? Who duffed one again. So let's suppose the sea bass, the Polish cannon, is attempting a 60 meter or 65.6 yard field goal. Does he have that kind of leg? Absolutely. What's his longest field goal? 63 yards. During the game, he used to intimidate people by guys practicing his 45-yard field goals, and he would line up for a 60-yard and kick a field goal over the guy's head. Anyway, so the ball leaves his foot, only 1 foot, at a speed of 31.3 meters per second at an angle of 48 degrees above the horizon. Crossbar on the goal post is 3.048 meters, i.e. 10 feet, off the ground, assuming no air resistance. Air resistance does make a significant difference, by the way. Will he make this kick? How can you even approach this problem? How can you answer? Go ahead. Okay, so we'd start with a picture. So we start with a picture. Go to here. Let's see, what information did we have? It's 48 degrees, 30, what was the speed? 34.3? 31.3? And equals, what is it? 3 point, I can't remember that either. 048? So we're going to check to see if he makes the field goal. How far can he kick a field goal with this speed? There's more than one way to solve this. Does anyone want to give me this is how I would start it? If you don't, I will start. The first thing to do in this is always, number one, add the thing that wasn't given me. Acceleration in the y direction is minus 9.80 meters per second squared. Show your x and y directions. That's always the first thing. Second, break the initial velocity into its components. So I have x direction, y direction. The velocity initial is equal to, in the x direction, I need to break 31.3 into the x and y components. So adjacent side is the x component. And I'm actually going to calculate those numbers right off the bat. Make sure that seems right. So I have my brain is there. 20.94 meters per second in the horizontal direction. And 23.26 meters per second in the vertical direction. So that's my speed information. Now we also have the y initial is equal to 0 in the x direction and 0 in the y direction. The x initial is equal to 0 in the x direction. Oh, not that was my mistake there. I can't believe I did this. I should have had my x in the x direction, it's 0. In the y direction, it's 0. I did write that correctly. It was the x final that should have been unknown in this direction and 3.048. Now, when I look at this, I have which variables I have in the x direction, which ones I have in the y direction. The straightforward way to solve this problem is to calculate how long it's going to be in the air. That is, I have the initial vertical velocity is 23.26 meters per second. It starts at a height of 0, ends at a height of 3.048, has a downward acceleration of 9.8 meters per second squared. I put that into the equation that has all of the variables and solve for time. That equation is going to have the quadratic. I'm going to have to solve it using the quadratic equation. What's the quadratic equation? If I have the form ax squared plus bx plus c equals 0, then x equals minus b plus or minus the square root of b squared minus 4ac all over 2a. Now you're going to have to use that equation, but I am going to cut this problem short by looking back at what it really asked me. It really asked me if he's going to make the field goal. And it gave me a distance. It gave me a distance of 60 meters. So what I really am looking for is if he kicks the ball when it's 60 meters down the field, is it going to be above or below 3.048 meters? So that allows me to use an easier way of determining if he's going to make it. It won't tell me how long a field goal he could make, but it didn't ask me what's the longest he could make. It'll just tell me if he will make it or not. So I'm going to come back to the problem and simply say, "60 meters, right? How long is it going to take for it to get 60 meters? Well, that's a simple calculation. Time was unknown, right? So I'm going to say for 60 meters in the x direction, there I put the kinematic equation with all the variables because I know them all. But acceleration in the x direction, what was the value of acceleration in the x direction? It's 0. So this is going to be, I forgot the time there. Do be careful with your work. So now I can solve this. Time is equal to x final minus x initial over v initial x, which is equal to 60 meters over my v initial x, which was 20.94 meters per second. And I have the time is 60 divided by 20.94, 2.865. So I found how long it's going to take for the ball to get to the goalpost. And now I just have to determine if it's above 3.048 meters, it's going to go in. It's good. If it's below that, fail. Because he wouldn't, well, you hope he wouldn't be offside side, but obviously that happens a lot. So now we just say y final is equal to y initial plus vy initial t plus 1/2 ayt squared equals 0 plus 23.26 meters per second times 2.865 seconds plus 1/2 minus 9.80 meters per second squared. That minus is very important because it's going down. Times 2.865 seconds quantity squared. And so we put that in the old calculator. Maybe. And we get a whopping, did I do that right? It seems, well, that the answer is 26.42 meters. It's still way up there at that distance, if there's no air resistance. Is that what other people got? Yes or no? Yes? Okay. Now, we will finish with our, well, we have to watch the video. God forbid we wouldn't watch the video. Which did work before class, so I'm trusting it still will.
I was just backtracking. Turn around. What? Because of this? You can make it. Make it? You mean jump it? No, absolutely not. No way, we're going back.
It can be done. This incline here is 30 degrees roughly, right? The car's the factory weight of the car is 60. Add all weight plus car, we're talking 2,100 pounds.
No.
If we hit this thing at 50 miles per hour, our trajectory will clear 10 feet. Easy.
No way, absolutely not.
Kyle, we'll go 60 just to be certain.
We're going back. This is impossible. No, you sure? No.
Of course I'm sure. With physics, I'm always sure, yes.
I'm driving. I don't think you guys heard me. This is my car, and we're not going to be jumping over any rivers. God, it's 10 feet.
Bob, don't jump this in a golf cart. Look, it's spinning across this gap.
Good. Yeah. Well, better make it 75. Okay. Yeah. So, 75.
No, you guys.
It's science.
Y'all, get out of my car. Kyle, in the car, come on.
We're okay. You know you can hit 60, right?
I'm trying. It's going to stop.
Thank you! What did I tell you?
The scene actually ends with him laughing and saying, I said it would make it. I didn't say that it would survive. What I planned was having you do the problem here to find if they travel at 60 miles per hour and the incline is 30 degrees, how far will they clear? I will ask you that question. Instead of doing a homework problem, that's the question I will have somebody do at the beginning of class next Wednesday. So go ahead and calculate how far they would actually clear in that case. And since I have 1 minute, I'll tell you. Okay, that's a clip from the movie Road Trip, which I cannot recommend. The first time I tried to do this in class was before YouTube was invented. And so I brought in the DVD to play. And the first, you probably didn't notice, you didn't see. But I cut off the first 8 seconds because it has an objectionable word in the first 8 seconds of this chapter. But I didn't have the sound running. I wanted the students to hear the whole, we've got this distance, this angle. If we go this speed, we'll make it. Even though you'll find that he should have done a better job with his math. They will make it, by the way. They'll make it way past this. Anyway, so I just hit the button to go back because I thought it'd take me back to the beginning of the chapter. And instead, it took me to the beginning of the chapter before it, which is a chapter where Tom Green is telling all the incoming freshman students about his fantasy of being in a woman's locker room. And so my whole physics class is watching that now. And it was a very embarrassing moment. Had to go talk to the dean. Cannot recommend that movie. All right, have a great long weekend.